Okay, another related rate problem. We have a man walking 5 feet away, 5 feet per second away from a light pole that is 12 feet tall. How fast is his shadow moving when he is 10 feet from that pole? So, where is his shadow? The tip of his shadow is right here. I would like to know how fast that shadow is moving when he is 10 feet from the pole. So what I'm going to do is set up a few pieces of information that I know. I'm going to label these. Everything in this problem must be labeled as either static with a constant or dynamic with a variable. And that's very important with related rates. You must know what parts are moving and what parts are staying still. Now, we're going to assume that the man is 6 foot tall. Didn't write that there, but that's an important piece. Man is 6 feet tall. Yes, we will assume that he is standing up straight. Or however hunched he is, he's hunching at 6 feet height. So, I'm going to label a few different variables. We may use some of them. We may not use any of them at all. Well, we'll use some of them. I'm going to let the first variable be the distance the man is from the light pole. That's changing because he's walking. So I will label that with an X. Though the question is, how fast is his shadow moving when he is 10 feet away from the wall? Well, if he stops moving at 10 feet, then his shadow's not moving at all. So he's just crossing through that 10-foot barrier, but he's clearly walking. Everyone okay with that? So clearly walking. Now, his shadow is, I'm going to call the distance from him to the shadow's tip Y. The distance from the shadow to the pole I will call D. Notice, I don't really want to know how fast the shadow is growing. I want to know how fast the shadow is moving. But that would be also an interesting question to talk about how fast the shadow is growing. So how fast the shadow is moving is that big distance rate of change with respect to time. Now, since the man's height is 6 feet, I'm going to go ahead and label that with a 6. It's a constant. It's never going to change in value. Now, I'm going to let the distance from the top of the light to the light pole, I'm going to label that as H, because that represents the hypotenuse of a right triangle. So I think those are most of the variables that we have. In this right triangle, I also have this smaller little triangle. This angle here is changing. I will call it theta. And notice I have two little triangles inside of each other. The triangle from the tip of the shadow to the man and up. The triangle from the tip of the shadow to the light pole and up. They both have two angles that are the same. Theta and a 90-degree angle from the man straight up 6 feet and a 90-degree angle from the ground to the light pole, both assuming 90-degree angles. Gives me two similar triangles. From that, I'm going to start to set up what I'm looking for and trying to find it with the given information. What I would like to know is D, the rate of change of big D. So we know that big D equals x plus y. So far, so good? Now, I know he's walking away from the light pole, so he's moving away from the light pole at 5 feet per second. The distance the man is from the light pole is x. So if he's walking away from the light pole, then x is increasing at a rate of 5 feet per second. So I know right now dx dt equals 5, or 5 feet per second. So what I'd like to know is how fast big D is moving, because big D is the distance from the tip of the shadow to the light pole. If I knew how fast that was growing with respect to time, I'm done. So here's what I'm looking for. I'm going to go ahead and take the derivative of this. Big D's derivative with respect to time equals, notice this was technically a 1 times dd dt equals 1, the derivative of x is 1, times dx dt. I'm using the chain rule because I'm taking the derivative with respect to time, not x, not distance, d, or y. So each time I use one of these variables, the derivative of y is going to be 1 times dy dt. I know what dx dt is. The only thing I'm missing is dy dt. So now that I've come this far, I need to figure out what dy dt is, because I can clearly see that this is a 5 plus dy dt. So somehow I have to have a relationship with y to the rest of the information I know. Where will I get that? I'm going to come back up. And I'm going to use similar triangle, knowing that y over 6, which is the cotangent of theta, is equal to d over 12. The cotangent of theta for the larger triangle. Same theta. So the cotangent will always be the same.
Do you have to split them?
Now, what I'm going to do is I'm going to get rid of that d. And I'm going to call this y over 6 equals x plus y over 12. I'm going to bring that information down. And now I'm going to multiply both sides by 12 to clear my fractions. And I will end up with 2y equals x plus y. And I took this equation here, multiplied both sides by 12. I'm now going to take that equation. What am I trying to find? dy dt. I need to solve this equation for y. So I'm going to subtract y from both sides. And something went, no. Y equals x.
That's because you have 12 and 6 and taking.
Which means when I take the derivative of this, dy dt is going to equal dx dt. And I know that dx dt is 5. So now I can do a substitution. And I have big dd distance dt equals 5 plus 5, which equals 10. And my top unit is in feet. My bottom unit is in time, or specifically seconds. So the length of this shadow is moving at 10 feet per second away from the light pole. We could also figure out how fast the shadow is growing. Actually, we did figure out how fast the shadow was growing. If you look up, that's how fast the tip of the shadow is moving, 10 feet per second. That's big D dt. If I want to know how fast the shadow is growing, that would be dy dt. How fast this is changing. So that would actually be growing at a rate of 5 feet per second.